We talked in an earlier learning video about the sun, so now let's talk about other stars. Stars basically are formed by gravity. They are huge amounts of mass that have been pulled together by gravitational forces. And if a mass of material gets big enough, it starts to perform nuclear fusion, just like we talked about with the sun. So the Earth isn't big enough, Mars isn't big enough, Jupiter isn't big enough, although if Jupiter were about 10 times bigger, it might have begun nuclear fusion. So whenever you just have a huge pile of mass, as long as it's big enough to start fusion, you have a star. So they really do exist because of gravity. For any star that's existing, there are two opposing forces working on it. There's gravity, which is trying to pull that star tighter and tighter, and then there's thermal energy from the nuclear reactions that's trying to push it outward. Here's a little sketch of a star. Gravity's trying to squeeze it smaller. Thermal pressure pushes outwards, trying to make it bigger. And once these two things are balanced, then we have a stable main sequence star. Let's start before that at the protostar stage. A protostar begins in a nebula, and we've talked before about how stars and star systems begin in nebula. Gravity contracts the cloud in the nebula, dust and gas comes together, the temperature rises, and eventually it starts to radiate long wavelength light, which is red. And then it becomes a protostar. Here's a figure from your textbook showing how we start with a huge region of nebula. This is 5,000 AU. Gravity pulls all of this material together. It starts to get bigger and bigger and bigger. And eventually we get to the point where we have an object that maybe is only 100 AU in diameter. And that would be, in our solar system, about the distance from the sun to Pluto. So still a really large object. The key to a protostar becoming a star is fusion. As gravity continues to collapse the cloud, the core heats up more and more, and eventually at 10 million degrees Kelvin, the hydrogen fuse into helium. This is called nuclear fusion. Again, the energy is released and pushed outward, balance is pulling inward, and we get a stable main sequence star. Remember that the main sequence is part of the HR diagram that spans from cold temperatures and dim stars to hot temperatures and large stars. With stars, it turns out that the bigger they are, the harder they fall, or I should say the faster they fall, because the biggest stars will burn their energy fastest and have the shortest lifetimes. The smaller stars will burn very slowly and can exist for billions of years. Let's look at the red giants. These are stars that are up here in this region. So they're very bright, but they're not super hot. And red giants occur at the end of a star's life. After the main sequence star has used up all of its hydrogen, it collapses, some heavier elements can form in the core, and the outer layer of the star swells and cools. And as it cools, it becomes red. And that's why these are red colored. Depending on how big the star is we start with, we either get a red giant or a red supergiant. Here's another cartoon showing these different stages. Number 1, burnup of hydrogen in the center of the star. For our sun, it's going to burn hydrogen for about 10 billion years. And you know that our star is about 5 billion years old, so we're about halfway through its life cycle. Then there's this collapse where the center becomes very hot and material falls to the core. There's an increased rate of fusion that takes place, energy expands, and the star expands to a much greater size. Here's a little cartoon of the sun today and what it will look like in about 5 billion years. It's going to be about 2,000 times brighter and 100 times larger. Is that going to engulf the Earth? Well, some people think maybe it will. Some people think maybe it'll just go all the way as far as Venus. In any case, we won't be around to see it. What about white dwarfs, these stars that are down here? Well, these represent the end products after the red giant phase of most stars. They're very small. Some of them are no bigger than Earth, but they're very dense, very massive, and very hot. A spoonful of a white dwarf, if you could hold it, would weigh several tons. Turns out that white dwarfs are made of something called degenerate matter, which is where the atoms have been squeezed so closely together that electrons have been displaced inward. This is not like plasma. This is a completely different material that we will never be able to put our hands on. White dwarfs aren't burning any fuel. They just cool off over time. Eventually, they'd become a black dwarf, but we don't have any of those yet in the universe because we haven't had enough time for white dwarfs to cool all the way to black dwarfs. So we've talked about the birth of stars before in nebula, like this picture here. And then life is basically on the main sequence, burning at whatever color that particular star is. The death of a star depends on its mass. So let's look at 3 different scenarios. For low mass stars, which are less than a half of the sun's mass, these are going to burn very slowly. They could last for hundreds of billions of years. And remember, the solar system is only 13.7 billion, so many of these have a long time to burn. They become eventually a red or a white dwarf. This little cartoon here is showing a nebula, a protostar, a main sequence star, and then eventually a white dwarf or a red dwarf. Medium mass stars have a little more going on for them. This would be between 0.5 and 3 solar masses, and they undergo the expansion and collapse of the red giant phase. They also then wind up being a white dwarf, but generally encircled with material called a planetary nebula, which is the material that was thrown out when the red giant expanded. Here's a picture of a planetary nebula with a star in the middle that's a white dwarf. This is going to be the fate of our sun. High mass stars, greater than 3 times the sun's mass, have a more interesting death. They have a very short lifetime because they burn quickly. They go through the red supergiant phase. And these stars terminate in a brilliant explosion called a supernova. And when a supernova occurs, what's left in the middle depends again on the mass. We either get a neutron star in the middle of the supernova or a black hole. And yes, a black hole is a star. So before we look at these 2 things, let's look at what was going on inside that red supergiant. This is where we have a lot of the elements being produced from the periodic table. Hydrogen, helium, oxygen, all the way down to nickel and iron. And that's because the pressures and temperatures are so intense that helium nuclei are being pushed together and fusing, nuclear fusion, with other elements to create heavier and heavier elements. Here's the periodic table with color codes for where the elements came from. So hydrogen and helium came from the Big Bang. And then everything that's in a yellow color came from small stars or can come from small stars. The green are things that came from large stars. And then all of the orange are things that come from supernova explosion. So we can only get the things up through green by this process. Then we need a supernova explosion. And the intense energy associated with a supernova is going to combine atoms to make all of the elements on the periodic table. Here is the remnant of a supernova that was actually observed to erupt in 1054. It started out as a star, and then the people at that time noted that it became incredibly bright, and in fact it was so bright they could see it in the sky in the daytime for months. Today we can look in that same location and we see this nebula that we call the Crab Nebula. So what's a neutron star? So as I mentioned, it forms from a supernova explosion, and this is a star that's squeezed itself very, very small because it's so massive. Only 6 to 12 miles in diameter. However, it is incredibly dense. The atoms have been changed. The electrons have been forced to combine with the protons to make neutrons. So this star is only made of neutrons. If we could take a cubic centimeter, which is about the size of a die that you would play a game with, it would weigh 100 million tons. And the gravitational attraction would be very dangerous on Earth if we had a piece of it. These also have strong magnetic fields and radio sources, and when these stars rotate, sometimes that magnetic field that's coming out of one side might pass the Earth and pulse as it passes the Earth. And so this is actually how these were found. So they're sometimes also called pulsars. Finally, a black hole. This is an object that is so massive and so dense, not even light can escape a black hole. Now, these were theoretical until we actually found some. As material gets pulled into a black hole, they emit a very strong X-ray signal. And one way that we can find a black hole is we can look for binary star systems. Now, I haven't mentioned these before, but more than half of the stars in our sky, if you look up, are binary systems. And what that means is two stars that are orbiting each other. In our solar system, if Jupiter had become a star, we would have a binary system. So here's a binary system in a cartoon showing a giant companion star to a black hole. So the black hole you can see is pulling in the material, and these jets of X-rays are going outwards and sometimes sweep by the Earth. This is one of the best ways we've been able to find black holes, is to look at companion stars that seem to be orbiting nothing. And then we can do mass calculations and figure out, well, there must be a black hole there. A strong candidate for a black hole is right in the middle of our galaxy, and it's called Cygnus X-1. This is a similar picture to the previous one, showing how a companion star's material can get swooped into a black star, and that can help us identify it with these strong X-rays. Here's the Milky Way galaxy, and in this box here is where Cygnus X-1 is. So overall, we've looked at the life cycle and death cycle of a star as it evolves on this diagram. Protostars start over here. They're bright, but they're relatively cool. And eventually they get hotter and they land on the main sequence. There they stay for most of their life, burning hydrogen. Eventually they go to the red giant phase, and so they get cooler and they get a lot brighter. And then eventually they move in this direction to get very hot. The core collapses, they become a white dwarf, and that white dwarf cools and dims over time. Coming up next, hundreds of millions of stars in galaxies.